Hello, I'm Ralf Eddinger from CANMORA Tech. I'm the president of the company. We are here for the first time at Rpid in Boston, showcasing our LEAM 1.2 3D printing machine for metal additive manufacturing. We are here to showcase our machine for the first time to a broader audience and demonstrate the capability of scaling our machines, which are actually specifically designed for increasing build volumes in additive manufacturing for metal components. So we are talking about meter class of machines with beds from 1 to 1 meter to up to 3 by 1.5 meter. So very large structures that can be built with powder bed fusion systems. In order to scale the technology, what we did is we developed a complete new setup on the machine, starting with a different tank technology where we actually fix the build plate onto the machine base and raise the tank above this build plate. So it's actually moving up and down. It's not the build plate. And the problem with the build plate is if we scale it up to large build plates, like in the meter scale, the weight and the deformation is too big to have it on a central shaft and then move it up and down. So we redesigned that, and we have a track system that actually allows us to build the tank as it goes up. And we can see that here as well. Second part is we use lasers that are not galvo-based. And the reasoning for that is the problem with galvo-based systems that have a changing angle of incidence on the surface will change the melt-pull reaction. So there are some issues with the melt-pull. So we always keep the beam perpendicular to the build plate. And another option for that is when we have multi-laser operations, we build gas chambers just around a single laser beam, and each laser beam has its own gas delivery and control system. That makes it sure that if we use up to 24 lasers in a machine, that they are not impacting each other, because that's one of the problems. If you only have one big chamber and you have multiple beams in there, they can actually impact each other. Another feature of this technology is we developed a different powder handling system. So we start with a tank that has a vibration-driven system, and then it comes out here. But this can be connected to any powder recovery through a pressure flange, and you can fill this up. So this is actually where you store the powder. And then this slot feeds it into a also vibration-driven feeding system. The vibration feeding system allows you to actually use powders that are very unconventional, from water atomized materials to superspherical materials. We even had nano powders in the system that also feed very well. What you would say in a conventional machine cannot be used as raw stock, feedstock. In this case, we can use that. So this is a very specific feature of the machine as well. The reason for that is to use lower cost powders, because we will need large volumes of powder, and we don't want to spend a lot of money with that. Under development currently, what we do is we have this plane, we call that plane as a print plane, but for certain components, we feel that a hybrid process is required. For example, if I need surface finish or tolerances that are beyond the printing process, we need to machine in process. So we created another layer, and that's under development, which basically has a machining spindle. It's basically an XYZ spindle with a tool changer and tooling, and you can then in process machine certain areas of your part. Available for specifically when you have features you need very precise that are not accessible from the outside after the part is printed. In order to produce the parts, we have actually an open source program which allows you to write in G code, which is normal CNC language, and program all the printing process in this open language. The code is generated from our slicing system, which we call CT-CAM. So CT-CAM takes then an STL file similar to what any slicing software would do, but the specialty on that is that we actually embedded the machine performance into the slicing process. So that means that we know the acceleration, we know the machine properties in the slicing software, so trajectories are corrected, and there will be no trajectories requested that would be outside of the envelope the machine can actually do. So sometimes you would say go on a corner, but no machine can go in a corner. So what we will do is we will calculate a radius that the machine can follow without changing the line energy in case the beam is on. And that's very important to maintain actually the quality of the print. Because if you just request trajectories that the machine cannot follow, the control system would actually change that. So we have a very fine-tuned interaction between slicing and then execution of the machine code. We want to develop your application. We are working on the machine design and all this, but we will need your input on the requirements so we can actually develop the specific application you're looking for. We can go into shipbuilding, we can go into aerospace, into tool and dies, automotive. We will work with you in order to develop the material properties you need, as well as the shape and geometry you're looking for in making your parts a reality.